proving the going down theorem. Let A to be integral domains, A integrally closed and B integral over A if P1 contained in P2 be prime ideals in A and Q1 be prime ideal Q2 I would say prime ideal such that Q2 intersection A is P2, then there exists Q1 prime ideal of B such that Q1 is contained in Q2 and Q1 intersection A is P2 P1. That means you start
in a statement A is integrally closed.
Yeah.
A is integral closure of A is A.
Yeah.
And you are saying that B is integral over A.
Yeah. So when you say A is integrally closed, it means it is integrally closed in B in the fraction field of A. So for example, if you take Z, this is integrally closed, but you have this is an integral extension, right. So integrally closed means Z to Q is no, in Q there is no integral extension of Z, but it could be somewhere else. Okay. So that is what we mean by this. B will not in fact be contained in fraction field of A. In fraction field of A there are no elements which are integral over A, but not contained in A. So B is integral over A. So I mean it says you start with a prime ideal chain here, and you have a in above P2 there is 1, then you can go down and get a prime above P1. So we were halfway through the proof. So enough to show that P1 B Q2 intersection A is P1. Okay. So we showed that if X belongs to P1 B Q2, then X is integral over P1, right. This is something that we showed yesterday. Now suppose X by S belongs to P1 B Q2.
So we started with X by X belongs
so this one, right. If X belongs to P1 B, then X is integral over P1. That is what we showed yesterday.
Yes, sir.
Right. Now suppose we have some X by S in the intersection. Now we wanted to say that this is, and this belongs to P1, right. P1 is contained here, so we need to show that this is in P1. Now S, see here S belongs to B, not in q2, right. So, first of all, this x belongs to p1b, therefore, it is integral over p. So, let us write x let x power n plus a1 x power n minus 1 plus etcetera a n equal to 0 be the. So, I will write this as minimal polynomial of or the minimal equation, minimal integral equation. Minimal integral equation of x over a. See, here one has to be slightly careful in the sense that, see, there exists a minimal polynomial, okay, for x over a. Suppose it is reducible. So, this is something that if f is a monic. So, this is, I will just write it as an exercise. A contained in B integral extension. We do not need integral extension itself. Okay. Let f be a monic polynomial sorry, this is only a ring extension because does not monic polynomial in f(x) in a(x). Okay. Suppose f(x) is equal to f(x) is equal to gx times hx. This is reducible in bx. Then the coefficients of gx and hx are integral over a. Okay. So, see, in this case I can talk about minimal integral equation, because if I take a polynomial, there exists, see, x is in PB1 and we have shown that it is integral over P1. So, I start with a equation. Now, if this is integral, if this is reducible, then I can write it as a product of two polynomials. Each one would be, suppose it is strictly small, I mean you can factorize into strictly smaller degree polynomials, then by this each element is in each element would be integral over a. These are all polynomial, these are all elements in P. So, I can say that if it is integral over a, it will belong to a itself. So, therefore, you can assume that this indeed is. So, I mean I am basically at each place, if you are reducing it to into a smaller polynomial, each one you can bring it back to a and assume there exists a minimal degree polynomial. Okay. I mean another way to see is, look at this ax. So, there exists ax to x. So, I have a kernel kernel has collection of polynomials, that will certainly have a smallest degree polynomial. If A is f, then it will be generated by one polynomial, but in this case we do not really have to worry about that. Okay, so let us come back to this. This be a minimal integral equation of x over a. Now that would imply, so see x by s, let x by s is equal to y, then I can write s as x y inverse as an element in fraction field of A. It will be in the fraction field of A itself, right, because y is in A, oh sorry, no, fraction field of B. No, what is y? Y is, sorry, y is in A because it is x by s is y. I am taking x by s to be y. Y is in A, x is in, oh, so this is in fraction field of B. But at the same time, see, s is in B itself. S is in B itself. So S is integral over A. S is in B, therefore it is integral over A. Last time we stopped here. Now S is integral over A, so S satisfies a minimal equation. See, again, if I have an equation for x, multiplying by y power the degree of this minimal equation, we will get a equation for S, right. So let me call this equation 1 multiplied with minus power n gives s power n plus a1 s power n minus a1 by y s power n minus 1, a2 by y s power n minus 2, an by y power n, this is 0. Suppose I have a integral equation for s. From here I can get an integral equation for x by multiplying by y power n. From here if I multiply by y power n, I get an integral equation for x. Similarly, given an integral equation for x, I can get a integral equation for s. So therefore, we can assume that this is a minimal integral equation if and only if this is a minimal equation, because you can from one you can get the other, from any one of them you can get the other one by multiplying by the correct power of y. So this is a minimal integral equation if and only if this is a minimal integral equation. Okay. Now, so this is this 2 is a minimal integral equation for s over k. K is okay. Now we use another property here. Again, I will state it. I will prove it. That is not very difficult. So this is the hypothesis. The first two lines same as going down theorem. A, B integral domains. Yes. A, this is integral domains A integrally closed and B integral over A. Let x in B be integral over an ideal I. Then sorry, this is fraction field of A itself. See why what are we saying? Yeah, let me write down this. Then x in B, x is algebraic over fraction field of A, and its minimal integral equation is given by x power n plus a1 x power n minus 1 a n equal to 0 with a I belong to. So, the see there is, it is integral over an ideal implies that there exists an integral equation with coefficients coming from the ideal, but the minimal relation we only can say that it belongs to the ring. Okay, if there are two I mean if it factorizes into two polynomials, what we know is that the coefficients will be integral over the integral domain A. Okay, but here we are saying that the minimal relation will be with AI's coming from radical of the ideal, not only from A, but it will be from the radical of I. If it is integral over an ideal, then the minimal relation will be with coefficients coming from the radical of I. I will prove this, but let us complete the proof of the going down theorem, and then I will come back to prove this. So here yeah, this x is x in B, x in B is integral over P1, this is what we proved in the beginning. So, the minimal relation x power n plus a1 x power n minus 1 plus etcetera a n equal to 0, these are with a I. Because of this one, we not only say that a i's are in A, but they are also in the minimal equation. Okay. So, we started with the minimal equation, each a I coming from a radical of P2, which is P2 or P2, which is equal to P2 itself. P2 or P1, this is integral over P1. That means each a I belongs to P1. Now what we have is y power, so this is a1, I mean ai by y power I. If I take this to be equal to ui, so let ai by yi be equal to ui, then what we have is y power I ui belongs to P1 we have this integral equation. Now S is, so this is again S belongs to B, we are applying this theorem again, S belongs to P and S is integral over A. So therefore the minimal equation, see this is the minimal relation, right. So therefore each ui is in A. Each ui is in A, what does that mean? Ui is in A and y power I ui belongs to P1. We want to say that y belongs to P1. If y is not in P1, that would imply that ui belongs to P1 for all I. Now we have this, what is the relation, what is the relation here?
Y or y power I?
Sorry?
Y power I does not belong to P1, same as y does not belong to P1.
Yes, y does not belong to P1 is a prime ideal. So y is not in P1, it is equivalent to saying that none of the powers. Okay. So if all the ui's are in P1, that would imply that this s power n, so I have s power n belongs to P1b, right. This would imply that s power n belongs to P1b, because you know s power n plus a1 by y, which is u1 x power n minus 1 dot 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 un, this is 0, which means x power n is minus of this, but this portion belongs to P1b. All the ai's are in P1, sorry ui's, all the ui's are in P1. So therefore s power n belongs to P1b, and that would imply that s power n belongs to P2b, which is contained in Q2, and that would imply that S belongs to Q2. But how did we choose S? S is in B without Q2.
Explain that part again, x power n belongs to P1b.
So we have the minimal equation, right? What is the minimal equation? For S. This S power n u1 s power n minus 1 plus etc. un is 0. This is the minimal equation for S.
Sir, one more thing. As you said, x belongs to be the integral over P1, then why the coefficients are same, a1, a2, an as coefficient for S, integral equation for S?
Which one?
This one, x belongs to be the integral over P1. So there exists an integral equation.
Yes.
But why the coefficient a1, a2, an are same as that for integral equation?
That's exactly what we are saying. So I have, what we showed is that, see, we are not only talking about the integral equation, we are talking about the minimal equation satisfied by x. Okay. So x is so some we have Px is a minimal polynomial. So let me complete this, I will come back to this. Okay. First this is over. So this implies that s power n belongs to P1b, which is contained in P2b, which is contained in Q2, and that would imply that s belongs to Q2. That is a contradiction. Therefore, s is in, sorry, the assumption is that y is not in P1, that is wrong. Therefore, y belongs to P1, and that says that x by s, that is equal to y. So, that says that P1b Q2 intersection A is P1, that implies P1 is a contracted ideal, and that is exactly what we wanted to prove. Okay. Now, let me get back to your question. So, here I have x in P1b. This is, so I can even just take x to be in B, whatever, is integral over A, in fact integral over P1. That is what we have proved. Okay. Now, let us look at this this result. This result says that x is, I mean this we can even talk, just take it to be B itself, does not really matter. X in B is integral over P1. Therefore, x is integral algebraic over the fraction field. Okay. And moreover, see what is meant by x is algebraic over fraction field. See, I have A, I have B. Okay. Now, look at the fraction field of A. And look at the fraction field of B. X is integral over A, and A is integrally closed, means x is not here to start with, x has to be here itself. So, therefore, I have a field extension and x in here is algebraic this, which means I have a monic polynomial, and for in the case of fields there is a unique monic polynomial which is satisfied by the given given element x. So, what we are saying here is that if you take that unique minimal polynomial, its coefficients come from the radical of this ideal. See here, if I look at, let me call this to be k. Now, I look at this k contained in kx. Okay, k, this x or whatever, both are equivalent in fact. If x is algebraic over k, then these two are same, this is same as kx, this will be a field in fact. If I look at this ring homomorphism T going to x, the kernel will be generated by, this will be a field, this is a PID, therefore, kernel is generated by a irreducible monic polynomial, and that is precisely the minimal polynomial of x by definition. Here what we are saying is that if you take that minimal polynomial, all these AIs are in radical of the ideal. So, in our case, now let us come back to our case, this is integral over P1, So, let me write this f x to be equal to x power n plus a1 x power n minus 1 plus etc. a n. If this is the minimal polynomial of x over a, then each ai belongs to the radical of p1, but that is same as p is a prime ideal, therefore that is same as p itself, p1 itself. Now as we saw, x power n plus a1 x power n minus 1 plus etc. a n, this is 0. Multiplying this by y power n, what we get is s power n plus a1 by y s power n minus 1 plus etc. a n by y power n. This is 0. Okay. Now see, if so s is in b, s is in b, therefore it is integral over a. Okay. Now again the same thing you can apply, it is integral over a if you take any integral equation of s. From that integral equation I can always obtain integral equation for x, and from any integral equation of x I can obtain integral equation for s. So therefore degree of minimal polynomial of x is less than or equal to degree of minimal polynomial of s, and similarly degree of minimal polynomial of s is less than or equal to degree of minimal polynomial of s. Therefore they are equal. Since they both are monic polynomial, they have to be the same. The polynomial, this is the minimal polynomial of s over a, and that is exactly what we are getting. Is that clear?